Hey, good morning. Yes, so let's continue our lecture. And we, I hope I can finish chapter 2 today. I hope. And then make sure that you know that everyone know that every friend or classmate nearby you know that uh next next Tuesday will be our quiz. We will have two problems from really similar to the problem I gave to you, announced in the Facebook club. Um, so if I were you, I would just practice all the problems, and then you will you will see the problems in the quiz really similar to what you practiced. Okay. I believe it will be 2nd of April. Okay, that's it. Um, so let's continue. Chapter 1 and 2. Okay, the quiz will be chapter 1 and 2. I will ask the teaching assistant to announce quiz information again in the Facebook club. All right, so let's continue our lecture. Yesterday, we uh, talk about this problem 2.611, and 2.611 problem has A, B, C items for each small problem. And this is C. Okay, so A and B were related to this one, the PQ incline section, but it was relatively easy, so I didn't mention here A and B. Okay, but this is a C. So C is the most difficult one, so I just mentioned here, and uh, there are two information I need to uh, edit here. And then I also highlight this plus X directions. Okay, act on the quarter of the length. So there will be the key later. We will use that later. And yesterday, sorry, and then we focus on the. We know that they increase 50 degrees C and locked between the walls, and the allowable normal stress is 23 megapascal, and shear stress is 11.3 um, uh, megapascal. And the problem want to ask what kind of force is the maxima we can apply at the quarter of length. What the value of this? Okay, and if it won't break, okay, and then under the 50 degrees C increment. So the value, the stress or the deformation we need to consider is the first one is 50 degrees C increment, and also delta 1 and delta 2. The delta 1 is the length, the deformation in the first section. Delta 2 is the second section, deformation of second section. Okay, and because we want to know the delta 1 and delta 2, we need to cut the first section, okay, to get the normal force N1. And so we just cut it. And yesterday, there's some students ask about the cutting position. Actually, I cut here or here or here or here. Within between the section 1, they are all the same. The result will be all the same because N1 will always the same between the section 1. N2 will be all the same between section 2. So I cut here. It's okay. I can cut here, 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 here. The result will be all the same. Okay, until here. I cannot cut here. I can only cut any cross-section between these 3/4L. Okay, so I just cut here and then I left-hand side to balance the force. I cut here, I left the left-hand side to balance the force. And remember that when we try to calculate delta 2, we need to use 3/4L, 3/4L, because the N2 act at the distance between this length, 3/4L. Although we do the free body diagram with longer, that is because we choose the left-hand side. Okay, so I believe some students asked me about this yesterday after the course. So I try to explain this in formally in this class. Okay, so now we have delta 1, delta 2, and the deformation about due to the thermal increment. And delta 1, delta 2, and thermal increment summed up together become 0 because they are limited between the walls. Okay, and then because of this, and substitute that, and we can have RA equal to blah, 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 blah. Okay, so this is RA. So we found the reaction force unknown, right? The unknown will try, when we know the RA, we know the N1. So N1 is this one, and N1 means the first section, right? So the first section, you can directly determine the sigma x. The sigma x is and which needs to be less than 23 MPa. No problem at all. That's good. However, when we talk about the allowable shear stress, when the shear stress in this material, the maximum shear stress will be half sigma x, right? So if the problem said the allowable shear stress is 11.3, which means that the sigma x equal to 22.6 megapascal, and sigma divided by 2 will be 11.3, right? So your sigma x cannot exceed 22.6. Otherwise, you will have shear failure. Okay, then you see 23 and 22.6. The 23 will always greater than 22.6. So which means that actually 23 megapascal is, useless in this problem. They just mentioned that, but we actually don't need to consider that because shear failure require your more attention on that. Okay, 22.6 megapascal. And don't forget, the tau max will have positive and negative because of that they are come in pairs. Okay, so don't forget this. Right, so let's take a look. I will copy sigma, this one. Copy. Okay, so next page. Let's continue. So so the first section okay, and sigma x equal to 3p/4a minus e delta t alpha, and which is really important, plus or minus 2.6 megapascal. Don't forget that it is positive or negative, right? Because shear failure determine everything. Okay. So let's continue. So sigma x could be positive 22.6 or negative 22.6. And both of the value, positive or negative, will cause maximum shear stress, right? So the P here, sorry, the P has two solution, positive 2.6 plus 11.4. The 11.4 is well, 11.4 is actually from here. Okay, is that correct? Sorry, 11.4. What is 11.4 come from? 6 11是从哪来的？忽然忘记了，脑袋忽然打结了。I'm sorry。11.4。哎，会不会就是11.4是什么？哦，E delta T alpha，应该是这个吧？应该是 E delta T 的 alpha 吧。Okay, let me finish that, and then we can examine that later. Yeah, I guess so. Yes, 0.00285. Okay. Okay, so I believe 2.6 MPa, and this one go to the right hand side. So this is positive E times delta T alpha, so it should be 11.4, and this one go here and times the area 0.00285. Okay, so this one definitely is that one. Okay, sorry, at first glance I forgot what's the value of this. And minus 2.6 minus a plus 1.4 and okay, so the answer here is 129,200 Newton. Oh, it's really long. Okay, and let me draw the problem again. Here. Okay, so why I don't need to calculate the second one? Because minus 2.6 plus 11.4 remain negative. So here, the P here, the P is negative. Okay, and which is not correct because the key said P is in positive x direction. So, okay, we don't need to calculate the second one because minus 2.6 plus 11.4. Okay, so this is contradictory. No. Okay. You need to be positive. Okay, so the first section required the P not exceed 129,200 M. Otherwise, it will have shear failure. The second section, it will be exactly the same. M2 plus P plus RA equal to 0. So N2 equal to minus P divided by 4 minus EA delta T alpha. Okay, and the sigma X equal to minus P for A minus E delta T alpha. Again, the second section is also the same material, right? So the material is still determined by the shear failure. not normal force failure. Okay, so again, plus or minus 2.6 MPa. Then we'll do exactly the same here. E equal to minus 2.6 plus 11.4. Okay, and times, you see, minus signs here, minus P divided by 4A, right? So here is minus 4 times 0.00285. This is the area. And this is minus 2.6 minus 11 plus. Sorry. Positive 2.6 plus 11.4. But now you times minus 4. So this P is negative. But above, because you times minus 4, you have 127,680 Newton. Okay, so in the section 2, you cannot, the section 2 require the P cannot exceed 127,680 N. If you exceed that, the second section will experience shear failure. Okay, so now which one we will choose? I believe I don't need to ask because this is easy now, because we are going to choose the lower one, because otherwise it will break, right? So this is the answer. Okay, so 127,680, and you know that the second part is weaker, right? It's weaker. The first section is stronger, weaker. So now you know the weakness was the second section. So the mechanics of material can help you to understand the weakness of a material, of the system. I think this is quite useful techniques. Okay, right? 有没有需要用中文讲一下？需要吗？那我快速讲一下哈，就是说哈，我们现在他是要问我们的 P 最多能就是下多少在上面，然后让这个材料不会坏掉，对不对哈？那这时候我们刚刚前面有讲到，就是说它这个已经增温了50度了，然后这时候我们又加上这个 P， 那所以你会有两段的力，因为它在这一段的状态力就会改变嘛，对不对哈？所以你会有两段的力，那两段的内力啊，N1、N2，那 N1 呢会造成这一段的 deformation，N2 会造成这一段的 deformation。好，然后呢，我们前面又说到，就是昨天蛮多同学来问的哈，就是我切这里，我那时候画不是切这里跟切这里嘛，但是实际上我切哪里都可以哦，只要在这一段之间，我爱切哪里都可以，因为我只是在画力平衡嘛，所以我切这边的时候，我留下左边，但实际上我可以切这里啊，我留下左边，其实力平衡答案会一样哦。那我切这里好了，一样啊，还是一样，力平衡还是答案会是一样的。所以说切哪里，只要在那一段里面，你要看哪一段，你就切哪一段。那一段的哪一个地方其实没差，因为它的力都从头到尾都是 N2 嘛，对不对哈？好，那所以做完切完以后，就把 N1、N2 算出来以后，就把 deformation 也算出来了。那当然了 ，deformation 就是第一段就是L，第二段就是L。OK， 你算了 delta 1跟 delta 2了。那这时候再把这两个式子带起来，你就会得到 RA 会等于用 P 表示的式子。OK， 那 P 表示的式子以后呢，等一下 ，P 表示的 OK，P 表示的式子以后，你就可以把RA 算就是写出来以后，你就可以跟 N1 扯上关系，所以你的 N1 就可以写出这样子的一个式子，N1 也跟P 有关了哈。那这时候 N1 当然就是中间第一段这个的内力，内力的话就可以算它的 sigma x。那 sigma x 的话，你就会发现它必须要小于23 megapascal。OK， 这个我知道了。那接下来呢 ，tau max 也是啊 ，tau max 就是这个材料 tau max 是11.3。那我们知道是 tau max 在最大的时候它是但它的值正好是正负1/2 sigma x。那时候我们就可以反推回来说，我们 sigma x 只要超过22.6 megapascal 就会有剪力破坏，那所以根本等不到23 megapascal 嘛，所以22.6 megapascal 就够了。就是我们要去要求的东西，不能超过它了，所以23根本就是白写的。好，那我们就看第一段，第一段呢就把它带进去啊，但是要写正负哦，因为你拉或压都有可能造成剪力破坏，因为正负，对不对哈？所以说我这个 sigma x 可以写正或负，都可以算一遍。那我们就算啊，这个 P 的代线啊，那刚刚我突然秀抖，不知道11.4是什么，其实就是这个东西了哈，E delta T alpha。好，把这个东西带到左边来，然后算出来是129,200。那另外一个如果是负的话，我们就会发现哦，它会变成是整个这边是负的，那负的乘上后面的正的，所以它的 P 是 negative， 表示说我们的假设是错的。哎，不对啊，题目已经告诉我们正 x 方向了，所以这个是不合题意的。OK， 好，那接下来 second part 就是做一模一样的事情，但是因为 second part 呢这边有一个负4a，所以说4a 分之负1负 P 了哈，所以这个负4乘上去以后，原本你刚刚是加起来是负的，哎，乘起来反而变正的。好，那正的反而变负的啊，所以 P 就是 negative， 然后就算出这个答案。所以这两个答案呢，选一个，当然是选 D 的那个 ，OK 就不会坏掉了。That's it. Right, next one, I will talk about the strain energy. When you apply a force on the spring, wow, okay, you press that, you will store energy in the spring. If you extend that, you will store energy inside the spring, right? Because if you release it, the energy will release, right? Converts to kinetic with the velocity, right? So strain energy is what we are going to talk about now. So when we talk about spring, actually everything in the world you can estimate it, see it as a spring, like this bar. That the bar looks like actually act like a string. Okay, so when you have the force applied, and you will have a delta deformation on it, although this is kind of exaggerate, 夸张了, okay? But when you do that, you store energy in this bar, okay? So typically, if we in the mechanics of material course, we typically say, okay, the force is increased gradually, slowly from 0 to P. Okay, gradually, slowly, without a sudden move. Okay, if you have sudden move, you introduce like the velocity or acceleration is that you have more force, more energy on that. But if you do that really slowly, each step you can regard it as an equilibrium state. Okay, it's the static load. We call that static load. It will be stable and easy for us to calculate. Okay, static load, 静态的负载. Okay, and then your P external force will thus work on the rod, 做工啦, and then the work is actually the underlying area of the delta and P force and displacement diagram. Okay, remember, I believe you learned that in senior high school, right? When you talk about the spring, you do this work to the spring because the spring was elastic, linear elastic. So you will have this kind of force and displacement plot, and your work is this triangle. Remember that? Half kx, right? Half kx squared, right? Remember that, right? So actually, if we write it down in a more general form, not not always linear elastic, right? They may have the some not elastic behavior. But anyway, the work is the underneath area in the load and deformation plot. Okay, and of course, because you do the work, you store strain energy in that material. Okay, if you apply work, the work is stored in the material. In the real ideal world, okay, ideally your work 100% stored in the material in the ideal world, okay? And typically, energy is joule, okay? That's it. So if we assume that our material is linearly elastic, so yeah, that's what I talk about. This is a triangle underneath the line, and you see the internal strain energy U equal to P delta divided by 2. Well, this is the area of the triangle, right? So U equal to W. In strain energy equal to the work you done on the material, and which is equal to P delta divided by 2. So the delta is P, and also delta equal to PL divided by AA. So you substitute that back, U equal to this one, P squared L divided by 2EA. Or if you know the delta, you have EA delta squared divided by 2L. So when you know the force value, you use this. When you know the elongation, you use this. Well, easy, right? And I believe you understand this because we just need to sum up all the section into all the internal energy, strain energy, strain energy in each section. So you do the summation for each section, you can have the total strain energy. And of course, if you have the gradually decreased cross section, your U equal to the integral of that each dx, right? So I believe you can accept this concept. Then I want to make some comments on strain energy. Okay, the strain energy is not linear function, which means that you cannot add them up straightly. Okay, what does that mean? You see, if you have the same material, you elongate one unit deformation, and you next one you do the elongation for 2 units, double the deformation. So this is the energy. This is energy. How about if you increase 3? So this is another deformation for the strain energy. Do you think U1 and U2 summed up together equal to U3? Of course not, right? So U1 plus U2 not equal to U3. Yeah, of course, right? Of course. Because you can see this area won't equal to the third one, right? So you cannot separately, and then, do the work separately and sum them together. You expect you do that at once. 就是你拉一跟拉二的能量加总起来不等于拉三的能量，就这样，哎，看得出来吧？哈，这个图案。Okay, so again, and also another comment is that strain energy is actually the type of potential. Remember that you do the elongation for the spring, you change the position of the spring, right? And then you release that, it will go back to its original shape. So you release that strain energy. So strain energy is related to the position. So it's a potential energy. When the energy related to the position, it's called potential energy. Okay, yeah, and when the bar or spring under compression or tension, they all store energy. They all store strain energy. So you can see here is delta square. No matter delta is positive or negative, after the square, everything is the same. So they store energy. Right. Next one will be this one is a little bit difficult. I would like to put some address on this. It's called displacement caused by a single load. Wow, this is a little bit need your imagination. When the material are linear elastic, okay, and subjected to a single load, only one load here. Of course, this one, this plot is exaggerate. Okay, so but actually this dash line should be that. Okay, it's really, really tiny. I put here, I draw this is just a bit exaggerate. So actually we can only considering the y direction deformation, because in the real world it's really, it's just like that. Okay, yeah，就是它其实夸张化了哈，你可能会觉得，哎，这边还要画一个三角形，没有，因为它实在是太近了，太小了，它其实应该是要这样子的，所以你可以想象，就是它的 deformation 还是就是变形还是只有 y 方向了哈，这是，对，大概是这样。Okay, so when you have a deformation along your force, the force and deformation has the same direction, okay? Which means that your strain energy will be equal to the work you done, of course, and the work you done is force times its deformation, right? So your UW equal to P delta divided by 2. Okay, so the delta can directly determined by 2U over P. So maybe you think, I know that already, but this is because I just want to let you know that if the problem is simple, it's in a relatively simple structure, you can directly obtain your strain energy by, you can obtain your deformations directly from the strain energy. Okay, although maybe you don't understand this, but it's okay. I will give you a example later. You will know that this concept will help you to determine the deformation. OK， 就是说了，因为你的力跟你的位移是同样的方向，所以如果你可以直接算出材料里面的 strain energy 的话，应变能的话，你就可以直接去除以它的这个带这个公式就可以。因为如果今天它很复杂，有两个方向的力，然后又有不同的就是你的应变能的来源可能会有两个力去贡献给它嘛。但是现在只有一个，那所以你就可以马上直接用 strain energy 直接帮助我们去带这公式，就可以把 delta 算出来。所以也就是说，简单的状况下可以用这个方式啊，可以用能量的方式帮你算出位移，还蛮有趣的。等一下就有一个例题告诉大家。Okay, next one. I would like to introduce another terminology called strain energy density, but actually they are very similar. Okay, strain energy density. Did you notice that strain energy is capital U, but now if you have density, you have small u. Okay, small u. The small u is that strain energy per unit volume. So you need to divide by volume. Your strain energy divided by volume. Okay, so you can imagine that if you have a prismatic bar, okay, and the volume will be cross-section area times its length. Okay, so your u, small u, will become the capital U divided by AL. Okay, so you can have this one. well, you can have this one, and you have sigma equal to P divided by A, epsilon divided by delta divided by L. Ta-da, ta-da. Okay, so you can have this one. And then you notice that U equal to U equal to 2 sigma epsilon divided by 2. Oh, so you notice that U is actually the plot, the area under sigma and epsilon, stress and strain curve area. Okay, so stress strain curve, force displacement curve, corresponding to strain energy density and strain energy respectively. Okay, so strain energy density relative to sigma and epsilon, but your strain energy well related to P, force and deformation. Okay, easy. Now let's continue. If we have 3 bar, the bar has different design. You have the prismatic bar and the bar with thicker head and tail. And even longer head and longer tail is thicker, okay, fatter. Okay, so let's determine under the same force P, and we want to see the strain energy stored inside. So the area here equal to pi d squared divided by 4. U1 equal to, well, U1 is really standard, right? So we just need to substitute the formula PL2E P squared L2EA. So this is U1. We just memorize it. How about U2? U2, sigma I equal to 1 N Pi squared Li squared Li and divide by 2EIAI. So each section. So P squared L divided by 5. Oh, sorry, I forgot to help you to do this. The middle part is L divided by 5. And the third case is L divided by 15. Okay? So L 2E8 plus P squared 4L5. The remaining part of that 2E. Okay, now 4A. Because you have double your diameter, right? So your area will be 4 times equal to P squared L divided by 5 EA divided by 2 phi U1. 2 over 5 U1. Interesting. U3. P2L divided by 15. The area 2EA. And the second part is P2 14L divided by 15. 2E 4A. Okay. 3P2L 20E8 310 U1. Okay, so you can see that under the same load, P, because of the shape, because of the design of the bar, you will have different stored strain energy. So you can see that number 3 can store the least strength energy among the three cases. Okay, so you can imagine that that one is the least material can store the energy. Well, it makes sense because it is stronger, right? It's more difficult to make it deform. When you have deformation, when you have strength, and then you will store energy. But you can see this is stronger. So it's more difficult for the same P to make it deformed. So the energy will be the least. Okay. Easy, right? Don't worry. The most difficult part of the chapter, the second chapter, has been passed. Okay. The rest of the part is kind of easy. Okay. Two problems. I don't know if I can finish that within 8 minutes. I don't know. Right. I suppose there's no problem because I think this is easy. Next one I will show you that strength energy cannot be superimposed, superposition 叠加 superposition cannot be superpositioned. Okay, next one. Ta-da. So there are one length. Okay, and let me take a look. Oh, okay. So here we are considering the weight density. So here itself has the weight. The bar itself has weight. So this one is purely the self-weight. The second case is self-weight and the force. Okay, so let's consider the self-weight, the first one. So what is the self-weight? Let's take a look. So how can we determine self-weight? We just cut it. Okay, we just cut it, and we just cut it. All right, and we cut at a distance x. All right, and the self-weight normal force, internal force will be n of x. Of course, the n of x will be the internal force due to the self-weight. Okay, and let's take a look. What is the value of the n of x? Easy, because this is actually L minus x. Right? So L minus x will be the self-weight, right? The L minus x material times its weight, that density will be equal to n over x, n of x. So n of x equal to gamma a L minus x, right? This is because the n over n of x will be equal to the material weight underneath, right? So L minus x times area times gamma. Okay, so the first one, okay, I will say the first one, and this is the second one with the pressure, with the force, right? The first one, u equal to 0L n over x squared. 好丑 n over square n of x square dx 2EA. Okay, and 0L gamma A L minus x by square root square 2EA dx equal to gamma square AL cube 6E. Okay, so the first one is easy, only self-weight. So this is a value. Okay, gamma 3, gamma square AL cube over 6E purely by self-weight. Okay, the second one. How about second one? NX. MX with the P, right? So now you will have second case. Dang, and this one, right? Second case. So it will be gamma A L minus X plus P. Yes. So U equal to gamma A L minus X plus P to EA dx. Okay, so after that, after the some integration, gamma square AL cube divided by 6E plus gamma PL square divided by 2E plus P square L 2EA. Okay, so did you notice that the composition of the answer? And this one. And ta-da! Okay, this is extra term. So you see these two cases, the first one is self-weight and this one is self-weight with the force. So the force, very simple, just like this, right? But the self-weight, the terms here, they are the same. But when you do that together, the strain energy cannot be superpositioned here and here with the extra term. Okay, that's it. 这应该听得懂吧？哈，就是不能把它叠加起来。当你叠加的时候，就会多出一个项啊，多出一个项。这是公式嘛，然后这是自重嘛，自重加公式不能这样加，多一个项。Okay, I guess I cannot finish this today. Only one problem left. So next Tuesday, I will finish chapter 2 and then continue to chapter 3. Okay, chapter 3 is relatively difficult. So if I were you, I will, take a look and please practice chapter 1 and 2 problems we announced. Okay, if you have any questions, just come here and I will try my best to help you. Thank you. 明天
的10点。
10点半。哎呀呀，有点糟糕。好，因为其实我有事。
哇，真的吗？那我要改吗？
看一下，没关系，我再跟你讲。
老师就是我这有跟您在上次的 meeting 提到，就是它那个 entropy 的最后一项，如果加一个常数的话，它就会交在那个300到400K 中间。
那个常数是什么？
然后我会有思考一个问题，就是那个常数的意义是什么？那个常数的意义就是在很接近0K的时候。